Good afternoon, everyone. I'm Zhang from ACUST. It's a real honor to share our work on the erosion mechanic load coupling behavior of aero engine blades. So let me walk you through the outline of my presentation. And I'll begin with the motivation. During takeoff and landing in dusty or desert environments, aero engine blades suffer from solid particle erosion. This leads to surface damage, aerodynamic losses, and even safety hazard. In recent decades, engine-related accidents have increased, with a growing proportion caused by blade erosion. This makes erosion a key factor limiting service life of aero engines. And in real operation, blades are subject to complex stress state caused by centrifugal forces and vibration, which generate substantial tensile stress. Such tensile loading significantly increases the material's sensitivity to fatigue damage. And indeed, several blade fracture incidents have been reported in recent years. Therefore, understanding the erosion mechanism load coupling becomes crucial for achieving long life and high reliability aero engines. To meet demands of high performance, lightweight design, and long service life, it is essential to develop erosion-resistant coating should prefer composite blades. Such coatings are already used in military engines, extending blade life by nearly 20 times. They also improve power output and fuel efficiency, offering clear economic benefits. Therefore, coating technology has become a key strategy to improve erosion resistance and ensure blade reliability. However, coating with high hardness or lick toughness, making them vulnerable to high-angle impact. Erosion involves multiple factors, environment, material, and particle properties, making single-layer coatings with simple structures can no longer meet protection requirements. So understanding erosion mechanisms and predicting service life under realistic conditions remain challenging. And to address this issue, our study takes a systematic approach from coating design and preparation to performance testing and finally to erosion mechanical load coupling analysis. The first part concerns coating design and preparation. We started with aluminum matrix composites, known for their high specific strength, which improve the thrust-to-weight ratio of engines. To enhance erosion resistance, multi-layer coatings that balance hardness and toughness were designed. In this work, titanium aluminum nitride on titanium coatings were deposited using multi-arc iron plating, meeting requirements for lightweight design and long service life. And we designed coatings with 4 layer numbers and 3 modulation ratios to optimize the stress-toughness balance. Each coating had a total thickness of 10 micrometers. After optimization, smooth, dense, and well-adhered coatings were obtained. All coatings showed over 4 times the subject hardness, and fracture toughness increased with both layer number and modulation ratios. Also, residual compressive stress further improved the toughness. Overall, the optimized coating exhibits excellent integrity and erosion resistance potential. Next, we evaluate the coating erosion performance. We built an erosion test system following the standard, using irregular aluminum particles at various velocities and impact angles to simulate real erosion conditions, providing a comprehensive assessment of the coating performance. The erosion rate, defined as the mass loss per unit eroded mass, was used as the evaluation index, and at 19 degrees, the coating with the 19:1 modulation ratio performed best. Further tests on coatings with this ratio, but different layers showed that the 10 micrometer coatings remained intact even after 1 hour of erosion at 200 meters per second. Among all samples, the 8-layer coatings with the 19:1 modulation ratio offered the best erosion resistance. And the surface morphology revealed that for uncoated subjects, shearing and pulling dominate at low angles, while indentation and cracking occur at high angles. In contrast, the multilayer coatings effectively reduce material losses, spallation and cracking across all conditions, demonstrating superior erosion resistance. 3D morphology also revealed that coating damage did not reach the subject. The failure process follows a layer-by-layer delamination mechanism, starting with surface wear, then stress transfer, microgravels, and local delamination, eventually causing spalling from surface inward. Compared with the subject, the optimized coating achieved over 719% high hardness and up to 4,250% better erosion resistance across impact angles. After clarifying the erosion failure process, we've moved from mechanisms to prediction because direct blade erosion tests are extremely expensive, and we combined multi-scale experiments and simulations to develop a quantitative erosion model, supporting both coating optimization and reliability assessment. Here we developed a numerical model replicating laboratory erosion conditions. Using clean erosion data, the model parameters were calibrated, and the erosion behavior of plates, cylinders, and simplified blades was simulated. And a conversion model was developed to transform erosion rate density into erosion rate, enabling quantitative comparison and prediction for complex shapes. The predictions agreed well with the experimental data. For plate erosion, error fell within a 1.5 scatter band. For cylindrical and simplified blades, the maximum error was 32.9%, which is significantly lower than reported in previous studies. This confirms the model's accuracy across materials and geometries. The fourth part investigates erosion mechanic load coupling. Using optimized coatings, we performed tests on the static and dynamic loading to assess performance under combined erosion and stress. Applying static load increased both erosion rate and the erosion depth, and similar trends were also found in the ductile subject. SM observations showed that the surface morphology changed little at low angles, but more defects appeared at high angles without altering the failure mechanisms layer by layer. Under erosion fatigue coupling, we compared the results from pure fatigue and the cupped test. As long as the coating was not fully penetrated, erosion had little effect on fatigue life. However, the coating itself slightly reduced the overall fatigue life, likely due to stress concentration at the coating cracks. The comparison of fatigue limits confirmed this also. Fatigue fracture surface analysis showed that for plate and cylindrical specimens, fatigue cracks most initiate from coating, reducing fatigue life. For simplified blades, cracks always started at the blade edge, indicating geometry driven stress concentration. And a key question is, how much erosion actually affects the fatigue life? To answer this, we test uncoated plates with controlled erosion depths. Results reveal a competition exists between manufacturing and erosion-induced defects. When the erosion depth exceeded 100 micrometers, fatigue life dropped sharply. Below that, the effect was minimal. And to capture this behavior, we proposed a life control parameter, including an erosion acceleration factor, and used as a weighting function to dynamically switch between dominant defect types, highlighting the critical defect size in fatigue life control. This unified model achieved a prediction error below 10%, demonstrating both accurate and general. We also considered axial tensile loads, which accelerate erosion damage. By introducing a tensile acceleration factor, we developed a new erosion model and software tool capable of predicting erosion performance under static load, under load erosion coupling conditions. Also, the software accurately predicted coating erosion rates within a two-foot gutter band compared with experiments. Validation with simplified bleeds. The maximum deviation was 30.9%, meeting the requirements for engineering accuracy. This enables efficient evaluation of bleed life under tensile erosion coupling. And in conclusion, this study established a comprehensive framework for erosion mechanical load coupling. We developed strong and tough multi-layer coatings, reviewed their erosion mechanisms, achieved accurate erosion predictions, and analyzed their behavior under realistic coupling conditions. These results provide an effective approach to enhance and evaluate the service life of compressor blades. Thank you for your attention. I sincerely appreciate the comments and suggestions from the experts and teachers.